Hello, everyone. Thanks for joining us today for another webinar in the Convergent Science webinar series. My name is Scott Davis, and I will be your moderator for today's webinar. We'd like to thank Convergent Science. Convergent Science is a rapidly growing computational fluid dynamic software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. During today's webinar, if you'd like to submit a question, please use the question box in your toolbar to the right and submit that question. All questions will be answered at the end of today's webinar. Today's webinar, titled Compressor Design, Reduce Cost and Enhance Performance with Simulation, will be presented by Amaya Waker, who earned his Master's of Science degree in Mechanical Engineering from University of Minnesota and currently works as at Convergent Science as a research engineer. So without further delay, we'll turn the time over to Amaya.
Good morning, everyone. I am Amaya Waker. I'm a research engineer at the New Applications Support Team in Convergent Science in Madison office. Today, I'll be presenting the work Compressor Design and how to reduce costs and enhance performance with simulations. So before getting started, what are the design challenges in compressors to begin with? So first is designing of compressors traditionally involves a lot of trial and error experimentation. Also, there is a high demand regulatory framework around environmental costs, especially greenhouse gases for compressors. Compressors have traditionally prioritized efficiency at cost of other factors like noise, actual material costs, etc. And on top of that, there are certain issues with experimentation as well. This uncertainty in experimentations can be very high. Certain intrusive devices that are used to measure the flow quantities can affect the flow field itself. There is a limited scope of image capturing techniques due to the complexities of geometries in compressors. There's also a difficulty in capturing the transient behavior and anisotropy of flow in compressors. It is also difficult to figure out the choice of location for transducer beforehand due to the availability of limited space and also not knowing where a lot of interesting physics is happening. And then on top of that, finally, there's the time and cost requirements for prototyping and building test rigs to run experiments on compressors. So what this leads to is that there is a significant amount of experimentation that goes in with only small knowledge gains and therefore leading to long design cycle times. So how can simulation aid this? Good simulations provide meaningful insight into the internal flow field of the compressor, as well as global parameters such as the mass flow rate and power consumption, etc. Simulation can also aid analysis of doing startup for compressors, wall design of compressors, analyzing noise and vibration in compressors. Also, depending on the type of compressor you have, CFD can also help you do multi-phase flow for lubricants. It also allows thermal design of various components, and finally do leakage analysis and figure out corresponding pressure losses and therefore power losses for compressors. So basically what simulation helps you is to cover a much larger design space with great variety of working fluid with significantly lower cost and engineering manpower. Of course, but there are certain challenges that come along with simulating compressors. The very first challenge is complex geometry and motion profiles can make meshing very challenging. As we know, almost all compressors have very complicated geometries and very small and tight clearances, so that can make meshing challenging. On top of that, the motion profile sometimes the motion profile cannot be captured with simple geometry motion types and might require some complicated motion profiles. There are also gaps with length scales which are significantly smaller than the domain size. That comes with its own challenges. Then also the challenge of modeling walls. It's not necessary that we'll have the wall motion profile available in advance. So there needs to be a way to model the wall motion. And finally, there might be certain uncertainty around boundary conditions. So although we would like to assume that the inlet and the outlet pressures are held constant throughout the experiment, it might not necessarily be the case, and we might have certain uncertainty around the boundary conditions. These are the main challenges that are present during compressor simulations. So how does CONVERGE tackle these problems? So for complex geometries and motion profile, CONVERGE generates mesh automatically and generates high quality Cartesian cut cells at runtime. And then mesh is also generated at every time step so that it can accommodate for the moving geometries. So here you can see an example of a scroll compressor where the mesh is being cut at every time step to make sure that the motion is captured accurately, and it will also make sure that the domain size and the domain volume doesn't change. So the next challenge, dealing with small gaps and small gaps which are significantly smaller than the domain size. CONVERGE offers two solutions. One is numerical sealing and another is porous media sink. So here is an example of a screw compressor on top of the meshing being automated, which helps to mesh those small gaps automatically instead of having to treat them specially. We can also deploy numerical sealing and momentum sink in form of a porous media. So here for screw compressors, we will have two tiny gaps. One is between the two rotors of the compressor, and another is between the rotor and the housing. And both of these are dealt with adding a porous media. The next challenge is modeling walls in case where wall motion profile might not be available. So what is the solution provided by CONVERGE? It's fluid structure interaction modeling, or FSI modeling. CONVERGE provides a very robust FSI modeling, provides very robust FSI modeling capabilities with allowing motions of up to 6 degrees of freedom for rigid body FSI. So here is an example for that. You can see this is an example of plate valve with 6 degrees of freedom. And we also have a ball valve here. You can see it is wobbling around as well. So that is a function of having used 6 degrees of freedom and allowing motion in all the three directions and rotation in all the three directions. So putting this all together, CONVERGE, we are presenting a case study for a novel spool compressor using CONVERGE. So what are the main motivation behind this type of study? So the TORAD spool compressor provides a new rotating compression mechanism for residential and commercial air conditioning systems. The essential features of this compressor includes a rotor and a constrained sliding vane, which will provide the positive displacement for compression. And we also have an array of poppet valves between the compression and the discharge region to allow the flow when the pressure is high enough. So we posit that CFD analysis in this case can be used to improve the design and the efficiency of the compressor. Since this is a validation study, we are validating our CFD model against measured data for 3 different operating conditions. So let's talk about the first step in setting up the CFD simulation, getting the geometry. So here is a schematic diagram on top left of the experimental setup, which was used to measure the data. So you can see there are a few different pressure sensors and the proximity sensor, which are used to measure pressure and volume, and finally used to create an indicator diagram for this compressor. And on the bottom left, you can see there is a internal schematics of this compressor. So based on this, we can extract the CFD domain using the CAD file. The CFD domain can be further divided into a few different regions. First is the suction manifold, where the refrigerant will be coming in from. We have the discharge manifold, where the refrigerant will be going out of. This is then we have the compression region, where the positive displacement will happen. And further looking into it, we can see that the essential features of this compressor are the rotor and the sliding vanes. And then finally, we have array of 9 poppet valves arranged as such. And this will allow the flow from the compressor region to the discharge region when the pressure in the compression region is high enough. So once we have the geometry set up, we can look into the operating conditions. We are currently validating the CFD model for 3 different operating conditions. We have 3 rotor speeds, and we have 3 cases with almost same rotor speeds and 3 different outlet pressures. So one is the low load condition, one is a mid load condition, and one is a high load condition. And we want to validate our CFD model for all these 3 cases. So once we have the CFD domain, now it's time to actually mesh the domain, figure out how our mesh will look like. So in Converge, it is pretty straightforward to give the mesh settings. You can see that it's about fixing 3 different values. One is adding the base grid. So this is the maximum size of the Cartesian cell that you are going to fill up your CFD domain with. So this is kind of a base grid, and everything else will be based off of this base grid. Then we have embedding. So this would be, in common parlance, it would be refinement. So what this does is it will add additional cells in location where you already know that a lot of physics might be happening. So in this case, that might be the rotor or the vane. So we know that a lot of physics will be happening around the rotor or the vane. So instead of using AMR, you can just add additional cells there just based on refinement. And finally, we also have AMR. What AMR does is it will add more cells only in the areas where we have high gradient. So in this case, we are using velocity based AMR. So whenever the velocity gradient meets the subgrid criteria, Converge will automatically add more cells in that region, allowing it to capture the gradient, the physics more accurately, but not at the same time not increasing the cost dramatically by adding cells throughout the domain. So how does this look like in action? So you can see we have a cut plane along the z-axis, looking into the compression region at a certain time step. So we can look at 3 different types of grid settings here. This is our base grid, the Cartesian base grid that we talked about. We also have embedding around the housing, the rotor, and the vane. So we see that there are cells which are smaller in size already present around the housing and the rotor and the vane. And you can also see AMR being activated here, where we have velocity meeting our SGS criteria. So here is a short movie that also depicts the same. So yeah, we can see how when the valves open and the AMR is being activated when the vanes pass over the walls. So it's as you can see, this is pretty simple. You can pretty much set up your mesh within less than 5 minutes, and yeah, it can give you a good quality mesh very quickly. The next challenge in this is valve modeling. So for this particular compressor, we did not have the valve motion profile available beforehand. So we used FSI modeling. And then for this particular case, we use rigid body FSI. So what are the assumptions that go into rigid body FSI? First is we assume that all the valves are point masses and centered at their center of gravity. Displacement is constrained in one direction. This is to replicate the actual experiments, because the valves are constrained by valve posts to move in only one direction, and we have one-way coupling between fluid and solid. What are the forces we consider that are acting on the valves? First is the spring force. Spring force is provided through additional variables regarding spring constants and spring constants, pre-displacement, etc. We also consider the body force acting on the valves, which is gravity in this case. And finally, once we solve for the fluid domain, we will calculate the pressure and viscous forces acting on the valve as well to basically get the total force acting on the valve. So here is an example of what the wall motion profile looks like for case 21 at when the case has reached cycle over cycle steady state. And here is what it looks like in action. So you can see once the pressure inside the compression region is high enough, we can see that the walls start opening up and they close once the vane moves past the walls. Next challenge is slip flow modeling. So in this case, we have three small gaps present in the fluid domain. First is the axial gap between the axial face of the rotor and the vanes and the axial face of the housing. And then we have two gaps in the radial direction. One is between the vane and the housing, and next is between the rotor and the housing. So we have deployed two different methods to deal with these gaps. For the axial gap, we use numerical sealing and remove the gap from the fluid domain completely. So what we do is we project the vertices on the axial face of the rotor and the vanes onto the axial face of the housing at every time step, and then remove that region from the fluid domain completely. And then second is radial gaps. So for radial gaps, we include this includes the vane housing gap and the rotor housing gap, and we use a momentum sink to account for two things. First is uncertainty in actual gap size. For this case, we have assumed that there is a fixed gap between the vane tips and the rotor housing, but this might not be the case in actual experiments. Certain vibrations might make the vane wobble around, and the gap between them might change. And second is, even though we have added refinement, the grid size around the gaps is still coarser than the gap size. This leads to unresolved viscosity, and which might affect our CFD simulation, and we account for that using our momentum sink approach or a porous media approach. So once we deploy all these models and run the simulation, we can start comparing our data with the actual measured data. So first we'll look at the indicator diagrams. So here we have indicator diagrams for all the three cases: case 21, case 26, and case 30. So you can see that we do a pretty good job at matching the indicator diagram or the PV curve throughout the CFD simulation. One thing to notice is there is a slight discrepancy for case 26 and case 30 towards the end of the compression cycle, but this is a function of that uncertainty of boundary condition point that I talked about in previous slides. What happened is even though we used a fixed outlet boundary condition in the experiments, the boundary condition at the outlet varied significantly, and the discrepancy we observe here is on similar order of magnitude of the discrepancy that we see in the outlet boundary conditions. So once we look at this indicator diagrams, it's time to compare the global integrated variables. So number one is the power. Since we match the indicator diagram pretty well, we can match the power calculations pretty well as well. You can see that for all the three conditions, our measured indicated power and the CFD indicated power are pretty close to each other, with the maximum discrepancy for case 21 of about 6%, and we calculated the CFD indicated power by integrating the PV curve that you observed in the previous slide. And also we can look at the mass flow rate. We can see that our mass flow rate is pretty accurate compared to the measured data, providing pretty similar volumetric efficiencies in both the cases. And the maximum error that we have for this is case 26, which comes out to be about 1.4%. So with that, we can make certain conclusions regarding the CFD model. So first is that the cut cell based autonomous meshing performs very well for complex moving geometries and without any engineering time that goes into the meshing. We also have a very robust FSI modeling for walls. We have various modeling options to treat the leakage paths. And then we were also able to optimize the computational cost by deploying two different tools. First is AMR to prioritize meshing in areas with high gradient, and second is grid scaling. This was you can reduce the cell count during the initial transient behavior so that you can flush out the initial transients on a relatively coarser grid, and then once the simulation starts reaching steady state, you can refine your grid or scale down your grid to a finer size. So based on this CFD model, later TORAD engineering, whom we were working with for this project, was able to identify that there were significant valve backflow discharge losses, and yeah, they were able to use our valve modeling feature to optimize the valve design. So they were able to save time and money by changing the valve design in the CFD simulations instead of running the building the test rigs and running the experiments. And they were able to go through a range of valve designs using our CFD tool. This also led to improved efficiency. You can see that they were able to change their valve design and increase their volumetric efficiency as a function of their pressure ratio, especially for the higher pressure ratio cases. And that basically helped them to improve their design before running the experiments. So yeah, this is what Greg Kemp, the founder and CEO of TORAD Engineering, had to say about our software and how it helped them to optimize their valve design and before actually building the hardware. Also, on top of what we have presented, we also have other capabilities which are very helpful for running CFD simulations, especially when it comes to compressors. First is, in addition to standard equations of state, we also have an option to use tabular fluid properties for a wide variety of refrigerants, and these properties are integrated with CoolProp. So you can see on the left, we can provide the standard equations of state that are available. Also, these standard equations of state might not be applicable for certain refrigerants that you might want to use, and we also, so for that we use tabular fluid properties, and we have full integration with CoolProp within our CONVERGE Studio graphic user interface. And also you can use refprop to get these properties and change the file format to match the format here and run the simulations with the data you get from refprop. We also have a very robust multi-phase solver with various interface tracking algorithms. So this is especially helpful for analysis of compressor condensation, lubrication, or oil cooling. We also have full 3D conjugate heat transfer capabilities for thermal analysis, and this is coupled with our super cycling feature, which accounts for different time scales that are present between the thermal flow, the thermal physics, and the fluid physics that happens. It gives us a pretty robust way to do thermal analysis without and also optimizing the time required for doing so. And on top of the rigid body FSI solver that we talked about in the previous slides, CONVERGE also comes with an FSI 1D beam solver for modeling deformable valves. So this is especially helpful for cases with reed valves. CONVERGE has full capabilities of solving reed valves within its software. We also have more 2D solvers in development currently. Also, finally, CONVERGE has an option to couple its software with external solid solvers. So a good example of this is the CONVERGE plus Abacus coupling for reed valve simulations. So CONVERGE will take care of the fluid side of the simulation and calculate the pressure and viscous forces acting on the valve, and these will be passed on to Abacus, and Abacus will solve for the valve deformation. We have very robust UDF or user defined function capabilities, and it can be added at any stage of the simulation. So here we see an example of UDF being deployed to basically demarcate our compression chamber into different regions where we can calculate the pressure volume curve based on how the chambers are being formed. So you can see that we will at any given time we'll have 3 different chambers in the rotor in the compression region, and we can use this feature to calculate the pressure and the volume of any given region, and thus help us build the indicator diagram. And finally, we have a very hands-on support team which will provide you end-to-end customer support, which also includes training your engineering teams and also doing consultation projects if that's what you are interested in. This is what Greg Kemp, the founder and CEO of TORAD Engineering, had to say about our support that we provided him while working on this project. With that, I would like to end the presentation and open the floors for any questions that you might have.